This video is about absolute convergence. So we basically have two things that we're going to be looking at, absolute convergence and conditionally convergent. So if it's absolutely convergent, then that means the series of absolute values converges. And so if that converges, so does our series. It's convergent. So we just call it absolutely convergent. Now, if the series converges, but the series of absolute values don't converge, they diverge, then we call that conditionally convergent. So if we can show that the series converges absolutely, then it's absolutely convergent. It's also convergent. If all we can do is show the series is convergent, then we call that conditionally convergent. So let's take a look at one. So we're going to determine if our series are absolutely convergent or conditionally convergent. They are all convergent. Those are the ones I've given. So if we take the sum from n equals 1 to infinity and we put an absolute value around it, if this series converges, then it's absolutely convergent. So let's see what we get. This would just become 1 over n. Since our n is greater than or equal to 1, the denominator will not be negative. It's going to be 1, 2, 3, 4. And so basically the negative is all we're removing. Well, we already know that that is divergent. That's our harmonic series, right? Our n is equal to 1 here. Sorry, not our n. Our p. Our p is equal to 1, and so it's divergent. But we know that the sum from n equals 1 to infinity of negative 1n minus 1 over n, we did this one in a previous video for our alternating series, this is convergent. And so the series itself is convergent, but the absolute value is divergent. That is what we call conditionally convergent. So the series itself converges, but not the absolute value of it. So this is called conditionally convergent. And it makes sense because if we look at this with Desmos, I've got them both plugged in. I've got the general term, or a sub n, without the absolute value, and then I have it with the absolute value. So that means the black here, right here, will come out for this one, and the blue will come out for our absolute value, or purple. I think I did pick purple. Yeah, purple. All right, so as it goes off, let's look at that again. You can see that the black alternates, and so the positives and negatives are actually adding up and canceling each other, giving us a convergent series. But if you take the absolute value, it's eliminating all those negatives, and so what we're actually doing is adding and adding and adding and adding, and this is just going to keep growing and growing forever. Therefore, the one with the absolute value diverged. It went off to infinity. And the one with the alternating, it converged. It went around positives and negatives, just kept adding and subtracting. And so by that adding and subtracting, it's converging. All right, let's try another one. So all we're doing is just placing an absolute value around it to see if it is conditionally convergent or absolutely convergent. And then we're going to modify it to make sure that it's always positive. That's it. So sum n equals 1 to infinity. We would just get rid of the top. The top would be 1. And then the bottom, the n is in front, and so this is always going to stay positive because, again, n is greater than or equal to 1 here. And then we can say, well, this is less than, oops, let's actually rewrite it. So we can now say that 1 over n cubed plus 1 is less than 1 over n cubed. And using our comparison test, the limit as n approaches infinity of 1 over n cubed converges from the p-series test, right? Our p here is greater than 1. So if that converges, the limit as n approaches infinity of the sum of n equals 1 to infinity of 1 over n cubed plus 1 also converges. And again, that's by the comparison test. Therefore, our series, the one that we're looking for, converges absolutely. And the nice thing about this is you don't even have to test the main series itself, because if it converges absolutely, it is also convergent. So this series converges absolutely because the absolute value of the sum, sorry, let's write it that way. the series of absolute values. So each term is getting an absolute value around it when you add them. And so that is converging, so that one converges. Let's look at it with Desmos. So if I hit play, you can see there it is. So the purple, the absolute value is converging here, right? And so is this one. So if this one converges, that means they're getting smaller and smaller. The things that we're adding to it are smaller and smaller. And so even though we're getting positive and negatives as we add these, they're both getting smaller and smaller. So it's converging absolutely, and it's converging by itself. And because it converges absolutely, it's absolutely convergent. All right, let's try one that's not an alternating series here. So sine n, you think, oh, well, sine does alternate. It goes positive and negative. Yes, but it's not going positive 1, negative 1. We don't have that pi in there. And so it's going to alternate between positive and negative values, but it's not an alternating series. So let's write it. N equals 1 to infinity. And so we're not going to be using the absolute value to just get rid of that. What we're going to be using it for is with a comparison. So we can say that the sine of n over 2n to the power of n is less than or equal to 1 over 2 to the n. And then that would become 1 over 2 to the n. So hopefully you can see what's going on here. Yes, we have a ratio. So let me move that over a bit. So when comparing the trig function, we can just use less than or equal to for it, right? And now we know the limit as n approaches infinity of the sum from n equals 1 to infinity of 1 over 2 to the n. Oops. This converges because our ratio of 1/2 is less than 1. So it's going to converge. So if that converges, then by comparison, so by the comparison test, the sum from n equals 1 to infinity, which I didn't need the limit up here. Just put that right there. There, get rid of it. Did I do it on the previous one? Okay, good. That one we didn't. Yeah, we don't need the limit here because I've already got the n equals 1 to infinity. So let's get that off of there. Of sine of n to 2n converges. And that means our series is absolutely, if I can spell today, solutely convergent. So if we take a convergent series and we put absolute values around it, and that absolute value of that series, the absolute value of the terms, the sum of the absolute values, converges, then we say it's absolutely convergent. And if that absolute value doesn't converge, then we would just say it's conditionally convergent. And if it diverges, it diverges. It's divergent. So that one's not something you have to really worry about right now. But just to test our work, you can see there we go that our purple, the one that is the absolute value, is also converging. And so they're getting smaller and smaller, the addition between those. And so also our alternating series is converging. So it is convergent, but because the absolute value also converges, it is absolutely convergent.